Module 3 homework. The first one is just checking that you can load StatCrunch. There's a few ways to do that typically. If this just says ask my instructor, if it says view an example or something like that, usually it has that. But usually there's a StatCrunch tab. We already practiced it in Module 1 and Module 2. A lot of times there are little rectangles that will populate data for you. I usually like to split screen so I can look at the questions, and I usually move the question list over so you can view more stuff, but this is just done, check, and we're all set. And then if you have more data, usually I'll just close this and leave it half screen because I know I'm going to have to switch back. Oh, I wasn't sharing my screen. Darn it. Okay. I forgot I unshared it to see if that was going to fix the audio issue. Thanks. Okay, so back to question 1. That's all that was open StatCrunch, click done, and then so try again, open StatCrunch, click done, click final check. That was it. All right, so everyone saw that okay? Hopefully. Okay, this one is just talking about a data set includes systolic blood pressure measurements from 147 adult females. If we compute the values of sample statistics from the sample, which of the following are unbiased estimators of the corresponding population parameters? I always forget this question. So like this one, I swear I Google it every time. I don't remember sample portion, sample variance, sample mean. Thank you. It's okay. Ashley, do you happen to know why? So why would they be? Yeah, because this one I always forget every single time. I just memorize it once a semester. Wait. So like, Okay, yeah. So when they use n-1 in the denominator, they're talking about degrees of freedom. It always threw me though, because the sample variance and the sample standard deviation are almost the same computation, except the sample variance is just the square of the standard deviation, or the standard deviation is the square root of the variance. So that always threw me a bit. Right. Oh, so the square root is what makes it. I don't know why that is though. So does it say here? Oh, because it's based on the sampling distribution. Okay. I think that makes sense. Sample means, sample proportion, sample variances are unbiased. Their sampling distributions have a mean that is equal to the mean of their corresponding population parameter. Ah, that's why. Because the sample standard deviation is going to change when we use a sampling distribution. So we're going to have to do the square root of whatever the standard deviation is that they give us divided by the square root of n versus the square root of n-1, as you just mentioned. So we'll see what that looks like when we get to some examples with some numbers. Like I said, for me, I'm kind of the worst at memorizing the terminology for the stat stuff. I'm usually better at just nuts and bolts getting into the formulas. But thank you for the clarification, Ashley. Fresher in your mind. Okay, so one thing is when you move to the sampling distribution, basically the mean always just stays the same. So because our regular population has a mean of 90, this thing is also going to be 90. The standard deviation here, what we do is we're going to take 6 and then divide by the square root of the sample size. So you can pull up a calculator. Let's say we open a new thing and we pull it down here and we do Desmos And let's just pull this down here. Okay, so math tools. We're just, and we know the answer is going to be 1, but your numbers again might be different. Again, you're just doing 6 divided by the square root of whatever your sample size is, which is here for me 36. So you can, I typed SQRT on Desmos to get that. There's also probably some way to get math symbols somewhere if you make this full screen. When you're typing. Yeah, so if you make it full screen, you can click over, there's a square root button right here. There's also something for functions if you need some more scientific functions. And you can compute that way. So for me, my sample standard is 1. And whenever you have that little bar, I know it's really tough to see that bar over the X, that's indicating that we're dealing with sample data and not population data. So really what's going on here, just big picture wise, I know we're just computing things and you may feel like you don't have an understanding of what's going on, is when you talk about a sampling distribution, when you talk about like a normal sample, like say 100 people, something like that, then you start talking about like person to person in that. You might have kind of like wild deviations. You know, like you might have like, if you looked at like heights of people, like a really tall person and a really short person or something like that. But what a sampling distribution does is it's not looking at individuals now as being groups of 1. Instead, it's looking at groups of different sample sizes. Okay, so like when you're looking at a sampling distribution, now you're looking at groups, you're grouping people into all these different groups of size 36. So like a group of 36 people out of a big crowd is going to have a pretty regular average height, even if it happens to have 1 or 2 tall people or 1 or 2 short people in it. So you're getting more regular behavior, and that's actually what the central limit theorem tells us is, you know, as you know, n approaches infinity, all of our distributions, as we take sampling distributions, approach normal distributions. So big picture, that's what's going on. Things behave more normally when we look at distributions of samples rather than distributions of individuals. Okay, and then this is again going to be something similar. So our mean, my mean is 79, so the first one I just copy down again, and then the second part I can just replace these. So my sigma, my standard deviation was 22. Now my sample size is 246, so I've got to change that, what's underneath the square root, to 246, and I get 1.40. And it says 3 decimal places, so I've got to do 1.40, and then this will turn into a 3. I typed 4 accidentally, so we get 3. Okay. Okay, again, a lot of words here, but we can just kind of scan and look for the key things. We know the mean is 7.5. So when they ask for the mean of the sample means, we know that's 7.5. That's just the same old thing. We don't even need to think when they ask us about the sample mean. So then they say there's a standard deviation of 0.34. That's our regular standard deviation. So that's going to be the answer for this first one right here. It's just talking about the regular distribution, the distribution of sample means. So we're not dividing by any square roots yet. So for this, for question 1 part B, our answer would just be 0.34 or 0.34. Okay. So then the second question is asking about the sampling distribution. Again, our mean doesn't change. That 7.5 that I have here stays exactly the same. I have 7.5. But then it gives me some key information. It says, so it says if n is 34. So in the second part, questions 3 and 4, my sampling distribution is assuming samples of 34. So to figure out the standard deviation of the distribution of sample means, what I want to do is I want to take my 7.5 and divide that by the square root of 34. and I get my answer. How many decimal places do they say? Hundredth, or hundredth means 2 decimal places. So 1.286 would round to 1.29. So that's that. Now they have a kind of conceptual question at the end here. It says, what happens to the mean and standard deviation as the sample size or size of the sample increases? Okay, let's just think about that. So far, the mean is never changing. No matter what we're doing, the mean is always staying the same. And if you think about what's happening based on the second part, well, if it's the regular distribution, the standard deviation is the same. But then as the sample gets bigger, we have a fraction where the bottom of the fraction is getting larger and larger and larger. So the bottom of the fraction being larger means the whole standard deviation is actually getting smaller. Like, let's imagine that we did 7.5 and then divided by the square root of, let's say, 90. Notice we went from 1.29 to 0.79. So it got smaller. So basically, the mean is going to stay the same, and the standard distribution of the sample means is going to decrease. So mean stays the same, but the standard deviation decreases. Did I say, it might say sample standard deviation or something like that. Wait, mean stays the same. What happens to the mean and standard deviation as the size? Oh, it says as the size increases. So if the size increases, the size of the sample increases, then the size of the standard deviation should decrease. What's... Yeah, it marked mine wrong though, didn't it? Oh, I didn't enter a part, so it's not marking this wrong. It's marking something else wrong. This should have been n was 34. Oh, for this one n was 24. So this should not have been 0.34. This should have been, so this one was 24 and this one was 34. That's what I had. My error was I should have been putting 1.53, 1 for the, or 2 decimal places. So I should have been putting 1.53 there. I did not see the n equals 24 when I did questions 1 and 2. Now everything should be okay. So when we're 24, we're at 1.53. When we're at 34, we're at 1.29. And mean stays the same, standard deviation decreases. What in the heck? Your answer is 7.5, 1.53. Is it? Okay, so... Oh, I put the mean, not point. You should have been 0.34 on top. Ah, darn it. I made a silly mistake. I put the mean on top and then divided by the square root of the sample size. It's clearly the standard deviation divided by that. So let me do similar and just run through it again. So we've got 7.8 divided by the square root. And I'm making the same mistake again. 7.8 is the mean, 0.36 is the standard deviation. So we want to do 0.36 divided by the square root of 25 for the first part, and then we want to do 0.36 divided by the square root of 36. And that gives us our two answers, so 0.072 and 0.06. So we get, and 7.8 was the mean. So let's answer all those questions again. 7.8, just real quickly, 0.07, just ask for 2 places. and then 7.8. And the second part was 0.06. And then mean stays the same and standard deviation decreases. So part C. Sorry about that. Lots of silly mistakes there. Okay, one adult female. One adult female means we're doing the regular distribution. So, and then they're asking for a probability here. So normally distributed, remember we're going to be using StatCrunch then. Actually, I'm going to leave this up because we're going to need the calculator when we move to the sampling distribution. So let's go ahead and open up StatCrunch. Again, you can go to Get More Help and do StatCrunch. And then from Module 2, we looked at how to find the normal distribution calculator. So that's what we're going to be using here. So to do that, you go to Stat, Calculator, and then Normal. Does everyone remember how to get there? Okay. So then we want to fill in our parameters. Our mean is that mu, 76. And our standard deviation is 12.5. And then let's see what question they're asking. So 1 means we don't have to do any messing around with a standard deviation because it's not a sampling distribution. It says find the probability that our pulse is less than 80. So standard is less than, so we do less than and we change this 0 to 80. And compute, and we get our probability. So 4 decimal places here, so mine would be 0.6255. Good. And I know I said halfway through we'll do attendance, but I'll just do it at the end since we're recording. So once we get through all the questions, then I'll go ahead and stop the recording and we'll do attendance at that point. Okay, now 16 adult females. Our mean will stay the same, and we've still got the same probability, but the deal is the standard deviation is now going to be different. So if I come over here, what I need to do is I need to do the standard deviation that I have right there, 12.5, and then I need to divide by the square root of the sample size it gave me, which was 16. Okay, so 16, and that gives me this number 3.125, and that's what I need to replace my standard deviation with, 3.125. And then I can compute my new probability. So basically, everything stayed the same for the second part, but I got a new standard deviation based on the sample sizes in my sampling distribution. So I can click compute, 4 decimal places here, 0.8997, and then the 2 doesn't round it up. So I just can do 0.8997, and I get my answer. Okay, why can the normal distribution be used? Okay, so there's some rules of thumb for using the normal distribution with sampling distributions. Normally, you want your sample size to exceed 30 to be able to use the normal distribution, and you also have some other smaller things if you read the text. But if you're already starting with something that's a normally distributed type of statistical distribution, then it doesn't matter. Any sampling distribution you're going to use is going to stay normal. So because it's already normally distributed, the sampling distribution is going to be normally distributed. So that's what it says here. Since the original population is normal, the distribution of any sample means is going to be normal. So that's going to be part C. That's a common multiple choice question that we're going to see this module. Okay, the rest of this is going to be very similar using the normal calculator. Remember, sometimes if they have us between two numbers, we have to come up here and switch between, and we've got 2 different values. So let's go ahead and plug in the mean of 195 is what I'm getting here. And then the standard deviation is 8.3. And then I'm answering part A, and I'm just kind of scanning and I'm looking for keywords, and I see greater than. So that means I changed this less than or equal to greater than or equal to. And then it says, what's the probability for 204.3? So I just do 204.3 and compute, and it should give me my answer. So we get, again, tricky parts for this. A lot of times mistakes are made because you have to really be careful with how many decimal places they're asking for. So I get 0.1313. So that 5 rounds that 2 up to a 3. Okay, so now on B, it says find the mean for 20 randomly selected. So that means n equals 20. So the mean's going to stay the same. We're going to have to do 8.3 divided by the square root of 20 to figure out our new standard deviation. So I'm going to come over to Desmos, the calculator, and do that in a second. But let's look at what the question is. The question is greater than 192.8. So let me do greater than 192.8 first. And then we'll come back and we'll fill in that last part where I have to do 8.3 divided by the square root of 20 and then fill that in. So let's go ahead and do 8.3 divided by the square root of 20. Compute. And then for these, you can kind of just do a lot of decimal places and you're probably going to be pretty good. So I'll just do maybe 4 or 5, 8, 5, 5, 9, 4, let's say. That'll probably give me enough accuracy. And if I compute, let's see if it did give me enough accuracy. I just need to enter 0.8821 because it says 4 decimal places, and the 6th and the 5th place rounds that 0 up to a 1. And again, it tells us the original distribution is normally distributed. So we'll all sample standard deviation, or all sampling distributions. And that's D for me. The normal distribution can be used because the original is normal. Okay. 4 questions left. How's everybody doing? A-okay? All right, again, these are all very similar. For a sample of 64, the probability of a sample mean being less than 24.1 is blank. Okay, so we're just filling in. Let's do less than and 24.1 because that's the question. And then what's the mean? The mean is 24. And now it tells us our sample's 64 and sigma is 1.24. So I need to do 1.24 divided by the square root of 64 or divided by 8. Again, it may be easier if you have a handheld calculator, but this is going to be 1.24 for me divided by the square root of 64. Which is 0.155. Let's see how 4 decimal places. If it's exact after 3, that should be enough. So I have to answer everything before it gives me the opportunity to check answer. The sample mean, I would say would not be considered unusual because it has a probability that is bigger than 5%. So less than 5% would be unusual. Larger would not be an unusual event. Oh, why is it telling me something about a z-score? Square root of n. Let me give this a quick read through. Find the required probability and determine whether it would give unusual. For a sample of 64, less than 24.1, mu is 24. So did I compute this properly? And what was my 0.155? I didn't compute properly. I entered the 0.155, the standard deviation, of the sampling distribution. I forgot to plug that into the normal calculator and then enter my computed number. So sorry about that mistake. My head is in the clouds today. So 0.74 and then 0.6. And then everything else should be okay. I don't think I made any other mistakes. Again, this is still a very big number, much bigger than 5%, 74.1% about. Okay, so my mistake there was I just jumped at the gun and entered the standard deviation into the problem rather than using it in the calculator to get the probability. Okay. Sorry about that. Again, a little rusty. I took a semester off of teaching stats and it's showing a little bit. Okay. So we have a mean of 60,500. So let's go ahead and just enter that. 60,500. Okay, so we've got our sample size of 30. And then it says less than 58,000. So that's the question we're trying to answer. We have to do... we have to figure out, for our probability first, the sampling standard deviation, which is 6,200 divided by the square root of 30. So we're going to go ahead and do that. 6,200 divided by the square root of 30. And then we enter that here, and then we compute. So that's going to be 1131.96. That looks close enough to me. And then we should be able to compute and use that in our problem. So we're getting a small number, so if they ask, this is probably going to be considered an unusual event. So 0.0136. And one thing that students always ask is like, why is it 5%? Why is that a magical number? Well, it isn't, and it is. It's kind of just like an industry standard for some reason, but people can be more specific when we get to different types of interval testing and hypothesis testing, and they can talk specifically about alpha levels that they want for defining unusual that are different from 5%. Okay, but this one's not asking that, so let's see. What are we saying? So this is the probability, interpret the results. Okay, so first of all, this would only interpret, we'd have to move the decimal 2 places, so 1.36%. So immediately we can rule out A and D. So it says, and the main thing, it says this is not an unusual event. That's a small number, so we know that this should be an unusual event. It's less than 5%, like we mentioned. So only 1.36% of samples of 30 specialists having a mean less than 58,000 is unusual. And again, as you group things together and look at their distributions, you start to have more regular behavior. So you wouldn't expect if the industry standard is 60,500. It wouldn't be uncommon for one individual to have a salary less than 58,000, but as you start to look at larger and larger groups, the means are going to get closer and closer to the regular mean for the whole population. Okay, so computing some z-scores. Z-scores are easy, right? Z is just let's get rid of StatCrunch. In general, let's write down the formula. Z is just going to equal x minus, see if, will it give me Greek letters / mu? Can I get Greek letters? Let me just do x minus mu divided by, it would be sigma. Do we have... No, I don't want a slider. I was trying to just get the Greek letters in there without appealing to another program. But x minus the Greek letter mu divided by sigma. I'm just going to write it using words because I don't see a handy dandy way to get a Greek alphabet. Yeah, not with these. I'm sure there's a way, but not worth our time right now. But anyway, we'll see in a second how we're going to do that. So to compute the z-score here, we have the average math score and the standard deviation. But the thing is, to move to the sampling distribution, we're going to have to figure out sigma, which is our regular sigma divided by the square root. So we've got the score of 554 divided by 513. So we've got our observation 554 minus 513. But what we're going to do is we're not going to divide by the standard deviation of 114. We're actually dividing by 114 over the square root of 60 because we want to know about the sample. Okay. So in general, the z-score is x minus mu divided by sigma, but for the sampling distribution, what's going on is we're basically doing the square root of sigma. And that's how it works for the sampling distribution, figuring out the z-score. So we're getting a z-score of about 2.78 or something like that, 2 decimal places, 2.79 if we round for mine. So this is a highly unusual event because 95% of your observations are going to be contained within 2 standard deviations. So once you're outside of that, then you're an unusual event. So is it justified? What was the claim? Claims that students have unusually high. Yeah, they do have unusually high. The z-score of 2.7 and the 8 would round to a 9 is unusual because it lies does not lie. It does not lie with the range of a usual event, which is 2 standard deviations. Okay, so let's review that. So when you have a normal distribution, and just, I wish I could show StatCrunch, but is there a way to do that here? Make this full screen. Only ask my instructor. All right. Well, I'll show the StatCrunch tick marks on another problem real quick after we finish this, but I'll show you why 2 standard deviations equates to 5%. But this 2.79 is bigger than 2, so that's what makes it unusual. So let's go back quickly to question 9, just so I can. Let's go back to. I just want to go back to a question where I can get a StatCrunch. You can do it from the book. I just don't want to. Let's go all the way back to question 1 because we know in question 1 we can certainly get to StatCrunch. Okay. So this relates to question 10. And I just want to show you if we went back to stat, calculator, normal, and we're just on the regular 0, 1. Let's say we did between -2 and 2 standard deviations. We're going to see that's going to come out to 95%. Or about 95%. So in general, they give the empirical rule says 1 standard deviation on either side is about 68%. 2 standard deviations is 95%, and 3 standard deviations is about 99.7%. So you can see from -1 to 1, you'd be close to 68%. -2 to 2, we saw was close to 95%, and -3 to +3 is about 99.7%. So that's known as the empirical rule when that comes up, 99.7%. So almost all the observations. Okay, so let's look and see what question 11 has to say. Last one. Okay, so we've got a bunch of stuff. We've got a sample of 70, and it wants the probability of a sample mean being greater than 216. So again, we want to go to the standard, and we want to say, okay, well, greater than 216. We know that's what we need to compute. What are our means? Well, our mean is 215, and we need to do 5.8 divided by the square root of 70 and plug that into my standard deviation. So do I still have Desmos back there? I sure do. So I want to do 5.8 divided by the square root of 70, and I get 0.6932. Okay. Sorry. That's the answer. I just wait. I needed to put that in standard deviation. Excuse me. And then this was 215.1, I think. Oops. Just wanting to go to the corner on me. Okay. Nope, it says greater than 216. Greater than 216, I'm sorry. All right, so mean is 215. Greater than 216, and the standard deviation we got by doing 5.8 divided by the square root of 70. So we compute that, and we get our answer that we can type in 0.074, and then 6. It asks for 4 decimal places. This is bigger than 5%, so this is not going to be unusual. It's about 7.5%. So this mean would not be considered unusual because it does not lie within 2 standard deviations because it's bigger than 5%. Okay, of course something's incorrect. 0.0746. Sorry. 4 decimal places. Did I round wrong somewhere? Okay. So for a sample of 70, the probability of a sample mean being greater than 216, mean is 215, 5.8 divided by the square root of 70, 5.8 divided by the square root of 70. Let's use more accuracy maybe. 0.693, 259. Let me just use more numbers and see if that does anything. I'm still getting 0.074. Sorry. Okay, so that is my... That is this. And then I computed. And I got this. 4 decimal places, 0.0746. 0.0746. Oh, greater means one-tailed. I'm sorry, that's what's going on here. So when you're single-tailed, that's going to bump it up to 10% because we're only looking in one direction. We're not looking. If you look at the previous problem, no, it was still greater than, wasn't it? The sample mean would not be considered unusual. I'm just thinking, sometimes single-tailed things get a little bit different. But I'm confident that this number's correct, I think. Just checking everything one more time. Sorry about all the windows. I should probably just do these both so I can see everything all at once. So 5.8 divided by the square root of 70 looks okay. Oh, it does lie. It does lie, right? Yeah. It's not unusual, meaning it's within 2 standard deviations. Yeah, sorry. My brain just completely blanked on that. So outliers are unusual, right? Outliers are the things that are outside the 2 standard deviations. So yeah, there was no problem there. I was looking for something different. When we get to hypothesis testing, well, the thing I'm thinking of is later in the semester, you start having these things with like your standard errors, and like you have to double them for single-sided single-tailed hypothesis tests versus double-tailed hypothesis tests. But that stuff isn't coming up this early, so I'm thinking too far ahead. Okay, so let me go ahead and just stop this recording. Okay.